Let's just dive right into this explainer, because today we are cracking open a century-long cosmic mystery. We are going back in time to look at literally one of the most brilliant scientific debates in human history. We're going to find out if quantum mechanics actually breaks the ultimate speed limit of the entire universe.
Think about it. For over a century, we've had this fundamental, unbreakable rule. Absolutely nothing travels faster than the speed of light. Period. But what if the universe has a hidden loophole? A loophole that actually allows action to happen faster than light, completely altering reality as we know it. We're going to investigate if quantum mechanics actually shatters the very foundation of modern physics.
To really get to the bottom of this mystery, it all starts with this strict rule called locality. Now, you probably know Einstein proved that gravity doesn't just act instantly across space. It travels, like a ripple in a pond, at exactly the speed of light. That principle, that effects have to spread from place to place at a maximum speed limit, well, that's locality. It is the absolute bedrock of Einstein's universe.
But you see, that deep, unwavering commitment to a local universe, it soon put Einstein on a collision course with the pioneers of quantum mechanics. In 1905, he fixes gravity. Amazing. But cut to the 1927 Solvay conference, and this brand new radical theory of quantum mechanics is taking center stage. And Einstein makes a terrifying discovery. He realizes the new math basically implies that particles could instantly affect each other across vast distances. And by 1935, this realization led to one of the most famous physics papers ever published.
All of this tension exploded into an epic and honestly pretty stubborn intellectual rivalry. On one side, you have Einstein, acting like the ultimate detective, desperately trying to save common sense and locality. He was absolutely convinced there were just hidden variables we couldn't see yet. And on the other side, Niels Bohr, this incredibly powerful establishment figure who was pushing a radical new philosophy. He said that a particle's wave function simply collapses instantly the exact moment it's measured, no matter how far away it is.
Bohr was just massively influential, and his view quickly became known as the Copenhagen interpretation. He essentially argued that physics should only be in the business of predicting lab measurements. He aggressively, and I mean aggressively, dismissed any questions about what particles are actually doing when nobody is looking at them. It was the ultimate shut up and calculate ethos. To Bohr, even asking what a particle was doing before you measured it was just a completely meaningless question. Well, Einstein wasn't having it. He fired back at Bohr with a really biting remark, calling Bohr's interpretation a tranquilizing philosophy or religion. And you really have to marvel at the audacity of Bohr's claim here. Einstein argued that Bohr's theory required a particle's wave function to collapse instantly across any distance whatsoever. Like if you measure an electron right here, the wave function instantly drops to zero everywhere else in the entire universe. To Einstein, there was no way around it. This was a terrifying violation of locality. It was spooky action at a distance, totally contradicting his beloved theory of relativity.
So to prove this faster-than-light non-locality was just mathematically absurd, Einstein and his colleagues Boris Podolsky and Nathan Rosen laid a brilliant trap in their famous 1935 EPR paper. They basically weaponized entanglement. Picture this. A high-energy photon splits into an electron and a positron. Their spins are forever intertwined. If one is pointing up, the other absolutely must be pointing down. Their fates depend entirely on each other.
Now, to explain how these entangled particles perfectly mirror each other without breaking the speed of light, Einstein proposed what's called a local hidden variable theory. It's actually a super elegant idea. He suggested the particles essentially pack predetermined instructions into little envelopes right before they separate. So when you measure the electron, it's really just like opening an envelope. It doesn't magically send some faster-than-light signal to the positron. The positron already had the opposite instructions waiting in its own envelope the entire time. Boom. An incredibly sensible, totally local explanation.
But here's the crazy part. Despite Einstein laying this perfectly brilliant logical trap, the physics community basically just shrugged. Bohr released this famously obscure, super dense reply that basically amounted to, yeah, there is no problem here. And because Bohr was such a dominant authority figure at the time, everyone just went along with it. They pushed Einstein's completely valid concerns into the shadows for decades. Fast forward to 1964. Years after Einstein had passed away, a theoretical physicist at CERN named John Bell dusted off that forgotten EPR paper. Now, Bell had always been pretty dissatisfied with the vague, hand-wavy answers of the Copenhagen interpretation. And during his sabbatical, it hit him. He realized that this grand, ultimate debate between Einstein and Bohr didn't have to just be a bunch of armchair philosophy. it could actually be tested in a real lab. John Bell cracked the case wide open with a totally brilliant twist to the old EPR thought experiment. Instead of just measuring the particles in one simple direction, Bell proposed giving the experimenters a choice of 3 distinct, completely independent axes to measure. Let's say 0, 120, and 240 degrees. This completely changed the game. It forced Bohr's quantum mechanics and Einstein's hidden variables to finally step up and make totally different mathematical predictions. So, the absolutely crucial point here is that Bell's massive, complex theorem actually boiled down to one incredibly simple metric: the disagreement rate. If 2 experimenters independently choose different axes to measure on, how often do these separated particles disagree? Well, according to the really bizarre math of Bohr's non-local quantum mechanics, that instant wave collapse would perfectly force the particles to disagree exactly 25% of the time. But, and this is a big but, if Einstein's common sense universe was right, and the particles were really just following those secret, local instructions hidden in their envelopes, the math proved they had to disagree at least 33% of the time. They literally couldn't fake it. The numbers were officially drawn in the sand: 25% versus 33%. It took decades, but technology finally caught up to the theory. At the Institut d'Optique, a scientist named Alain Aspect actually managed to perform this seemingly impossible experiment. Using insanely complex setups with entangled photons and rotatable polarizers, scientists literally put the universe on trial. They needed to see which number reality actually preferred, the quantum 25% or Einstein's local 33%. And the experimental results? Completely stunning. They perfectly matched the 25% disagreement rate. Einstein's local hidden variables were just dead wrong. Non-local, faster-than-light influences really, truly do exist in our universe. It forced John Bell to this startling conclusion, and I quote, "We are obliged to invoke something like actions going faster than light." Okay, now you might be wondering, wait a second, if this spooky action totally breaks Einstein's relativity, shouldn't that lead to some disastrous time travel paradoxes? Because think about it, in relativity, if you can send a signal faster than light, different observers will disagree on the timing. That means you could theoretically send a message back in time, where the effect happens before the cause. Total chaos, right? So how do we build an uneasy truce with relativity here? Fortunately, reality actually holds up. And here's why. Because the outcome of a quantum measurement is just totally random noise. Sure, measuring your particle instantly collapses the distant partner particle, absolutely. But you can't control whether you get a plus or a minus spin. Because it's completely random on your end, you can't actually harness this entanglement to send a coherent text message or any useful information faster than light. Even with this little truce, the fact remains: the universe still behaves non-locally behind the scenes. Einstein was entirely right to be worried about this. Which brings us to a final, really mind-bending question. Given how desperate physicists are to unify quantum mechanics with general relativity, which, by the way, they still haven't been able to do yet, is there any possible loophole that saves Einstein's dream of perfect locality? Incredibly, yes, there is a loophole, but it requires the ultimate twist: the many worlds interpretation. This theory just completely throws out the problematic instant collapse idea entirely. Instead of the wave magically forcing a distant particle to do the opposite, reality itself splits. Both outcomes happen, meaning there are now parallel versions of you experiencing each one. It's a pretty stark contrast when you think about it. Under the traditional Copenhagen view, the wave collapses instantly, making our one single universe undeniably non-local. But with many worlds, there is no collapse, because every single possible outcome creates a branching, parallel reality. The particles never actually need to communicate with each other faster than light. This is the ultimate loophole. If many worlds is true, that massive century-old tension between quantum mechanics and general relativity just vanishes into thin air. The universe is perfectly local after all. Your distant partner's particle doesn't need to instantly receive some faster-than-light text message. There are simply 2 versions of that particle, perfectly waiting for 2 parallel versions of your friend. It actually obeys Einstein's universal speed limit perfectly. So I'm going to leave you with this provocative thought. Einstein was terrified of action at a distance, and Bell proved mathematically that it exists unless we fundamentally rethink reality. To finally prove Einstein right and protect the universe's ultimate speed limit, are you really ready to accept that infinite versions of you are experiencing every possible reality right now? Thank you so much for exploring this wild, mind-bending mystery with me on this explainer. Keep questioning everything, and I'll catch you next time.